We consider the second part, equivalent systems. Let's say these two linear systems, 3 by 3 linear system. So the first one, the first equation is 3x1 plus 2x2 minus x3 equals minus 2. The second equation is x2 equals 3, and the third one is 2x3 equals 4. So see from this form, you can easily solve its solution, right? Because from the third equation, you will get x3 equals 2. And from the second equation, you will get x2 equals 3. Substituting x3 equals 2 here and x2 equals 3 here, immediately you can get x1. So the first system is very easy to solve. Okay, and now we look at the second 3 by 3 system. So for this system, at first, you may think it's difficult, it's not easy to get a solution. But in fact, later we will show that the system B, in fact, the second one, have the same solution, minus 2, 3, 2, as the system A. So they are equivalent systems. So what are equivalent systems? The definition is like this. Two systems of equations involving the same variables are said to be equivalent if they have the same solution set. So now we look in detail for the second system. So we can see that in system B, the first equation is the same as the first equation in system A. They are same, right? And for the second equation and the third equation, from the second system, how can we get such simpler form as A? So if we add the first equation to the second equation, we will get here is x2 equals 3. See, we just get x2 equals 3 here. And if we have x2 equals 2, and how can we get this third equation? 2x3 equals 4. So we can do the summation of the second equation and the third equation, right? We can get x2 plus 2x3 equals 7. And before, we already get x2 equals 3. So substituting x2, immediately you will get this term, 2x3 equals 4. Although the two systems, they look very different, however, they are equivalent systems. Okay, so one idea comes here, right? For general linear system, we want to have a simpler form, which can easily give you solutions. So in order to transform a general linear system to a simpler form, we use those operations. So we have three basic row operations. The first one, the order in which any two equations are written may be interchanged. So this means you can change the order of any two equations in the system. And the second operation is that both sides of an equation may be multiplied by the same non-zero real number. So given you any equation, you use a non-zero number, you can multiply to both sides, so you get the same essentially, right? And the third operation is a multiple of one equation may be added to another. So this means those two linear systems, they are equivalent. So the first, the I0 is ai1x1 plus TL plus ainxn equals bi. The j0, ajnxn equals bj, right? And if you use a scalar alpha times the I0 and then add the j0, those two equations, they are same, right? The first equation, the ith equation, they are same, of course. From this equation, if you use minus alpha times the I0, then add to the new j0, you will get the previous one, this j0, right? And of course, from these two equations, you can have these two equations hold. So they are equivalent. So now, in order to transform a system to a simpler form, we may have three operations, three ways, right? The first one, you can interchange any rows, any two rows, right? The second one, you can multiply a non-zero real number to both sides of an equation. And the last way is a multiple of one equation can be added to another. And in fact, we like this form, this simpler form, triangular form. See? So a system is said to be in triangular form if in the case equation, the coefficients of the first k minus 1 variables are all 0, and the coefficient of xk is non-zero, k equals 1 till n. So like this. So see this example, this is a 3 by 3 system. So for the first equation, you have non-zero coefficients for all x1, x2, and x3. For the second equation, the coefficient for x1 is 0, okay? And for coefficients for x2, x3, they are non-zero, okay? For the third equation, the coefficients for x1 and x2 are 0. Only the coefficient for x3 can be non-zero. So this system is in triangular form. Now, we have this result. If an n by n system has exactly one solution, then using operation 1 and 3, we can transform this system to equivalent triangular system. So triangular system corresponds to a unique solution. If we have the linear system in triangular form, then we can use a back substitution method to get its solution. So after reducing the system into an equivalent triangular system, the solution can be derived using back substitution. Okay, so see this example. So this is a system which is in triangular form. Okay, so immediately we can find x4, the value of x4. So x4 equals 1. Okay, and substitute x4 equals 1 here. In the second equation, you will get x3. So 4x3 plus 3 times 1 equals 3. So x3 equals 0. Okay. After you get x4 equals 1, x3 equals 0, you substitute in the second equation, you will get x2. Right? So x2 just equals minus 1. So using the value of x2, x3, and x4, you will get x1. So x1 you can solve as 1. Okay, so when the system is in triangular form, using back substitution method, immediately you can get the solution to this linear system. Okay. So now we consider solving systems of linear equations. So if a system is not triangular, we will use operations 1 and 3 to try to obtain an equivalent system that is in triangular form. Given you a general linear system, you want to solve it. So you think you want to make it a simpler form, especially the triangular form, right? So you can use the row operations 1 and row operation 3 to try to approach triangular form. Okay, this is example 3. Ask you to solve this linear system using 3 row operations. Okay, so the problem is here, a 3 by 3 system. So the first one is x1 plus 2x2 plus x3 equals 3. The second equation is 3x1 minus x2 minus 3x3 equals minus 1. And the third equation is 2x1 plus 3x2 plus x3 equals 4. Okay, keep in mind we want to transform this system to triangular form, so we keep the first equation unchanged. We keep this one, just keep this one, and we want to make the coefficient of here x1 in the second equation to be 0, right? And we also want to transform the coefficient of x1 in the third equation to be 0. So we use the third row operation. We just use 3, multiply the first equation, then add minus 3 times the first equation, then add the second equation. Then you will get this linear equation. So it is minus 7x2 minus 6x3 equals minus 10. And you can do this further, right? You use minus 2, this multiplier, times the first equation, you add to the third equation. So you will get, here is minus x2 minus x3 equals, here is minus 2 minus 6 plus 4, so it's minus 2, right? So you will eliminate this coefficient to be 0, okay? And later, because this one is non-zero, okay? You can use this non-zero number to eliminate the third equation, the new third equation, with the coefficient for x2 to be 0 again, okay? So you will get this form. After you get this form, see, it is in triangular form. You want it, right? We get it. So this form is easy to solve. From the last one, you will get x3 first. x3 equals 4, okay? From the second equation, after substituting x3 equals 4 here, you will get x2. So x2, you can find is minus 2. And substituting x3 equals 4, x2 equals 2 to the first equation, you can get x1 here. x1 equals 3, right?